Welcome to another unit in this methodology toolbox. This time I want to talk about the more classical approaches to regression analysis. So which different types of models do we actually have here? Well, if we start with this, the easiest approach, the most commonly known approach regarding regression is linear regression. We try to fit our data to a linear line. The next one, which is actually not so much more complicated, would be log linear regression. Here we're working with an exponential relation. So our data is actually exponentially distributed. Log linear already is like the first step, so to speak, in the direction of nonlinear regression analysis, whereas nonlinear is much more sophisticated. It's much more harder to actually pull off than a log linear regression, which is simply a small retransformation of the data. So nonlinear regression is the more general term for any type of model relations, any type of modeling structure which we use, while, and that's usually an assumption here, all the variables are still metric, are still continuous. If we relax the assumption of continuity, especially for our dependent variable, the easiest case we can get is that our dependent variable is dichotomous, meaning we only have like the possibilities 0 and 1. If we have something like this, we're going to use a logit or probit regression approach. If we have more than two possible answers for the dependent, we can use a multinomial logit or probit approach. It's like if we have 3 possible outcomes, 4 possible outcomes, something like this. And, well, with logit and multinomial logit, for example, we assume that data is, well, first off, not continuous, but that those values 0, 1 or 0, 1, 2 are also simply representing different outcomes, which not necessarily can be ordered. In other words, this could be something like country of origin, which I cannot order with larger, smaller, something like this. That's why I use the multinomial logit. If I can order this, so in other words, if I no longer have a nominal discrete dependent, but an ordinal dependent variable, then I can use a so-called ordinal or ordered logit or probit regression. This works particularly if I have ordinal data. Can still order them, but cannot yet calculate means or something like this. If I go one step further, meaning I continue, I might have metric data, but not necessarily continuous metric data. And I have different other possibilities. The first easiest possibility would be if I work with count data. Count data means basically that my dependent variable takes only values which I count off. So in other words, it's integer. It's something like 0, 1, 2, 3, 4. And in most cases, you only work with positive integers. So really like starts at 0, 1, 2, 3, 4, 5, 6, and so forth. In these cases, you can use a Poisson or a negative binomial model. Might have to check whether you have too many zeros in your model. Then you have to consider a zero inflated model, zero inflated Poisson or zero inflated binomial. But that's a different story. Here the main idea is working with count data. And then, well, even if we assume that we have continuous data, metric continuous data, it could be the situation that my dependent only takes a certain interval of values. So for example, that I only can get positive outcomes, that negative outcomes are not possible, not realizable in the model, are no valid answers for the dependent variable. In this case, I would work with centered regression models, or as often used in finance, with topic models. So for example, if you want to include like a measure of risk as dependent variable. Measures of risk oftentimes are built around the concept as with the variance. The variance per definition is positive or rather non-negative. So here you would have to work with censored data because negative answers are not possible. Meaning here you still would have to use a different model than the classical linear approaches. And finally, we have some specific cases where additional effects come to play. That could be if your data is spatially integrated with each other. So if you have, for example, data from different countries, and you can assume that there are interactions between the countries. Those who are much closer to each other interact much stronger than those which are further away. And that those effects might impact the results of your model. So whenever you have to include these spatial effects, then it makes sense to work with spatial regression models like spatial error, spatial lag models. Again, that's a different topic which considers these particular problems. The fact that, for example, the dependent variable is spatially linked to other values. Also, I already mentioned in the context of zero inflated data where we have too many zeros, as with count data, that we, for example, use the zero inflated models. That's a specific type of multi-step regression models. So whenever you have different steps one after another, for example, if I ask the question, how well do startups perform? Well, first off, I have a step where I have to explain what is the chance that the startups in my sample actually made it through the first, let's say, 5 years. I only have startups which are 5 years or older. Then I have to have the first step, what is the chance? So how can I explain what impacts whether startups make it through the first 5 years? And then, under the assumption that they make it through the first 5 years, what are actually factors impacting their success, their returns, something like this. But in this case, I might have a multi-step model, like a Heckman model, which I use. That would be a different approach. And finally, we have the so-called quantile regression models. Before, we usually assume that all our coefficients are constant. So with regression analysis, I estimate the coefficients of my regression line. I assume they're always fixed, they're always the same. That's also because, well, underlying the method, I'm working with averages, I'm working with the mean. That's when you take a look how, for example, method of ordinary least squares work. That's basically going down to working with means. That's also why we need an assumption like we do not have any kind of heteroscedasticity. Of course, this would assume that in different parts the line might behave differently. If we actually relax this assumption, say, well, it might be interesting to take a look how the smallest 10%, the next 10%, and so behave, and then get an feeling whether we really have a development trend which is linear for the whole data set, or maybe we have like a combination thereof, that something happens, like usually the relation is linear, but for the top 20% it looks differently than for the bottom 80. That's something which we can study, for example, with quantile regressions. So in other words, quantile regressions is a nice tool to allow us to test whether the assumption underlying linear regression actually holds true, or we rather should work with more nonlinear approaches. So this helps us ascertain, does the linear approach actually make sense? And it performs an alternative view on this. As I said, linear regression works with means. Quantile regression works on the basis of more or less a median. And well, we also know means are more susceptible to outliers than medians. So if you actually have to do a regression and you have to include outliers into your model, might consider quantile regression because it's less susceptible to outliers. And well, that's then everything there is. All the different approaches to regression analysis I wanted to show you here in this context. Of course, there are still more approaches. This is just a first overview, a first impression, what you might use in different situations. So I hope you enjoyed this overview. I say goodbye and see you next time.